Hello AP 8.6. Now that you've learned how to draw Lewis structures, now the topic is, can a structure be drawn more than one way? And it's called residence structures. If you can draw one way, it's simply moving bonds around. So we sometimes encounter molecules and ions in which the experimentally determined arrangement of atoms is not accurately described as a single dominant Lewis structure. So for example, one of the easiest type of molecules is ozone, and you do need to know the name of ozone. You're going to learn in chapter 9, it has what's called a bent shape to it, because now once we learn how to draw them in chapter 8, in chapter 9, we're going to answer some questions about their shape and their angles and hybridization and so forth, so forth. So right now, you're just seeing that it has a bent shape. Because each oxygen atom contributes 6 valence electrons, the ozone molecule has 18 valence electrons. Okay, so remember, it needs 8 times 3, so 24, but it only has available 18. So when you do the math, subtract, divide, it's got 3 bonds. But you have oxygen 3 times, so one of them has to be a single bond and the other one has to be a double bond. So this means that the Lewis structure must have a single and a double. However, this single structure cannot be itself be dominant because it requires that one bond be different from the other. Contrary to the observed structure, we would expect the double bond to be shorter than the single bond. And that's very important, as we just looked at how many electrons that they share. So in drawing the Lewis structure, however, we could just as easily as put the double bond on the left side. So right here looks kind of like the same image, maybe even like a mirror image. And sometimes resonance structures are. If you kind of hold up like a mirror next to the structure and draw the reflection. And when I first started teaching chemistry, I taught a class called ChemCom, which is kind of like the chemistry for students that struggle with math. And it was like the CP version before CP. And I would have students take out a mirror and have them draw what they saw in the mirror. And it really helped them. Okay, and if you struggle with this, do that. Put a mirror up to the picture and draw what the mirror is showing you. It's a very cool way to do it until you can actually see it. So there is no reason for one of these Lewis structures to be more dominant than the other because they are equally valid representations of the molecule. So the placement of atoms in these two alternate but completely equivalent Lewis structures is the same. But what happens, the point is, it's this last part. You can't move atoms around in resonance structures. All you can do is move electrons. And with those electrons, you can move lone pairs and bonds. Because remember, bonds are electrons too. So we call it resonance structure, where it's an attempt to represent a real structure that is a mix of several possibilities. Okay? Resonance structures are Lewis structures that differ only with respect to how you place the electrons around. So the true arrangement is basically what we call, it's a blend. It's a hybrid of them. So what we do is we draw what's called a double arrow, but a double-headed arrow. Please, please, please do not confuse it with equilibrium. Equilibrium looks like a double arrow like this. Oops, sorry, can't even draw an arrow today. Double arrow like this. That's equilibrium. This is the arrow for resonance. So what you do is you draw one structure, and then you draw another structure where all you have done is moved electrons around. So even though that double bond went from the left to the right, that's still electrons that moved around. So please remember, when you move those electrons around, only bonds and lone pair electrons can move. Okay? You cannot change atoms' positions. Okay, and I know it's kind of hard to see that with just 3 oxygens looking at it, but you know Rodriguez has more examples. So the resonance structure is this double-headed arrow that you draw in between, and you have to figure out how many possible structures it can have. The majority of the time, I don't think I've ever seen past 3 or 4 possible structures. Okay, never seen anything past that. But you have to figure out what that's going to be. So molecules such as ozone cannot be described as oscillating between the 2 individual Lewis structures shown previously. There are 2 equivalent dominant Lewis structures, okay? Because if you did the formal charge for it, you have this structure and this structure. They're both dominant structures. Only because you got oxygen 3 times, okay? If we had other atoms in it, then we'd have to calculate formal charge. So you have 2 equivalent dominant structures for ozone. Ozone always has 2 equivalent OO bonds whose lengths are intermediates between singles and doubles. This is what happens. This is very important right here that you understand what I'm about ready to say. Let's say right here you had that double bond on the left, but you could also have the double bond on the right. So what you see is something like this. Okay, so with this double bond, you have what's called a second order bond, because that's a double bond. But single bonds, oops, let me move around there, are called first order bonds, because they're singles. But what happens with resonance structure, what you sometimes you could see a picture like this in a video or a book, is you see like this dotted line that goes from this way to this way, which means you don't have a double and a single, you actually have a blend, which is called 1.5 on each side. So instead of telling me you have a double, a second order on one side and a first order on the other, remember, it's a blend. It's a hybrid in between the 2 structures. Right there. It's a blend of the 2. So one side is not more dominant than the other because it could be on either side. So experimentally, this is AP talking to you. Ozone has 2 identical bonds, whereas the Lewis structure represents 1 single bonds are longer, and a double bond that's shorter. Based on these 2 resonance structures, it has an average of the 2 structures. So what we do is we describe the OO bond for ozone as 1.5 instead of a first order and second order, as in a single and a double. If your structure can do resonance structure, it's a blend of the 2 structures, okay? Anybody else has whatever bond that they have. So if they cannot do resonance structure, like water, for example, cannot do resonance structure. You can only do resonance structures if you actually have doubles and triple bonds. And I'm going to make sure I write that in just a second. Water has no doubles or triple bonds, so there is no possible resonance structure. So what if I ask you, what are the orders of the bonds? Well, this right here, they're both single bonds. So both are first order bonds. And if you're asked to explain, because they're single bonds. It's pretty evident right there. So only doubles are second orders, and triples obviously are third orders. Okay, so make sure if you're asked about bond order, which you did see a little bit of this in 8.3. So bond orders, before we actually start practicing, bond order, you have first order, which would be single bonds. And if you have second order, then obviously double. And third order, then obviously triple. Okay, so bond order, that's what it is. But because of resonance, for ozone, it's a blend. So it's 1.5 on each side. Okay, so key fact with resonance structures, can only resonance exist, this is a big part, if you have what's called multiple bond orders. As in, do you have double or triple bonds? Okay, so somebody like CO2, CO2 can definitely do resonance, okay? And I believe in the video we showed that before too, okay? So with that, I don't think I have CO2 on here. So with CO2, let me kind of clean this up a little. Here we go. We'll do it right up here. With CO2, when we drew it in the previous video, the math showed us that we had 4 bonds, okay? And lone pairs on these oxygens, okay? But who says that's the only structure? Why not? Why can't it be a triple and a single? So then you draw the resonance structure. And what happens is, let me show you a little drawing of the arrows, and you do not have to show AP how to do this, but I'm showing you what's happening. So what happens is, one of these, one of these bonds right here, sorry, my thing froze on me. One of the double bonds on one side is going to come over and create lone pairs, and then one of these lone pairs are going to come in to create a triple bond. Don't have to show me that. Just draw me what the picture shows you. So here's oxygen, triple bond, carbon, single bond. But remember, everyone still has to have the octet. Right now, oxygen is looking at 6 electrons. So you need only one set of lone pairs. And notice the lone pairs, they're going to move to get out of the way. Carbon still looking happy right now. Still has his 3 bonds on one side, 1 bond on the other. So that's 8 electrons. But now this oxygen is going to have 3 lone pairs. Okay, it's about moving electrons around. You cannot move the oxygens and carbons like you want to put all the oxygens on one side, carbon on the other. It doesn't work like that. But who says the triple has to be on the left? Why can't the triple be on the right? So I'm out of room, and please don't ever do this on a test or anything. You would draw another structure. Oh, and it kills me. I can't do that. I got to erase it. And then now put the single bond on one side, oops, and the triple bond on the other. Okay? It's literally a mirror image of this last picture. So if you put a mirror up to this, you draw what the mirror shows you. So now single bond has 3 lone pairs, and now this oxygen with a triple bond only has 1. So you draw 3 resonance structures because it has 3 blends, 3 hybrids of the structures. So instead of it having a first order and a third order, what happens is it actually has a blend between the first and the third order, which means it's a blend of a double and a double, a second order and a second order. And we know that because we did the resonance structure, I'm sorry, we did the formal charge calculation. We did that on 8.5's video. So we know this one right here is going to be the dominant preferred structure because of formal charge tells us that. Okay. So let's see how this works. So that way you can figure out how many to draw. Okay. Draw all possible Lewis structures for the following molecules or ions. So the NOS method works, and I would truly use it to your advantage. So we have NOS, we have carbon and oxygen, but don't forget, we're going to be gaining 2 electrons. So everyone needs 8, oxygen times 3. So 24 plus the 8, 32. Now remember, that's what they need, but what do they have? Carbon has 4 valence, oxygen 6 times 3. But remember, it gained 2 electrons. Okay, and I'm just circling it so you see what I was doing there. So 18 plus 2 is 20 plus 24. We're going to subtract, and that's a 4. 8 divided by 2, 4 bonds. Okay. Anytime for NOS, ladies and gentlemen, do it in the margin so that way it doesn't kill paper like I'm kind of killing space right here. So who is the center of the universe? Well, it's carbon. It's always carbon. So we're going to put carbon in the middle, and we have to put 3 oxygens around it. Okay, so I always put 2 of them on the sides, and you can put 1 on top or the 1 on the bottom. But I got 4 bonds. I have to have at least a bond in each location. So now I think you're seeing what's going to happen. One of these 3 is going to have a double. And maybe I choose this one, and that's fine. But now the name of the game is octet. This oxygen is looking at 4 electrons, so he needs 2 lone pairs. This oxygen is only sharing 2, so he needs a lot more lone pairs. And this oxygen is the same as the one on top, so he needs 3. Now look at carbon. Don't ever forget the central. Carbon's looking at 2, 4, 6, 8. 8 electrons surrounding him. He's looking pretty good. Lastly, because he's an ion, you got to put him in brackets with that -2 on the outside. Can this be drawn another way? Absolutely. Okay, so you got to draw your resonance. So now maybe I take this bond right here and I can move one of these over to a set of lone pairs, and then maybe we'll move one of these lone pairs in to a double bond. Okay, I'm just showing you what happens. You don't have to show me the formation of it. So now this carbon, oxygen on top will have the double, and then these 2 on the sides will have singles. And you just got to make sure you fill in your lone pairs. Okay, carbon's still not going to have any, and then -2. Can I do another one? Yep, I can move the double bond now down to over here on the right. Some students think it's tedious. It's like, oh my gosh, it's the same thing. Well, it's really not, because you have a double bond on one side versus another. It's about perspective. And because it has options, that means it matters. So we got to show every detail of every representation. Oops. All right, so I have my -2 charge on the edge, so that means I have 3 possible resonance structures. Okay, which one would be the dominant structure? Unfortunately, with this one, there would not be a dominant structure because they all have oxygens on the outside, and that double bond just moved one across the other. But you would have to check that, and I will show you when you need to check it and when you don't need to check it. Usually when you check it is because you have maybe different atoms surrounding it, or you have like 2 doubles and trying to figure out if a single or a triple is better than 2 doubles. Okay, that's usually what happens. Right here I have a double and 2 singles. The resonance structure, the formal charge is going to be the same for all 3 of those. Let's do SO3. And I'll do my NOS over here. Actually, let's do it on the bottom so I don't kill space. And sulfur and oxygen. Now this one does not have any charge, so I need 8, and then 8 times 3. So 24, 24 plus 8. And I'm doing math in my head right now after a long day. Sulfur, so please check my math. Sulfur is 6, oxygen is 6 also, so 18. 18 plus 6 is 24. And it looks about the same math as right above 4 bonds. So you probably figure out what's going to happen. It's almost going to look just like carbonate sitting right up there. 3 oxygens, and I have to have a bond between every sulfur first, but then 4 bonds, somebody's got to be a double. So maybe I just start the double over here. Literally the same thing. Question is, does sulfur need lone pairs? Sulfur is looking at 2, 4, 6, 8. He's got 8 surrounding him, so he will not have lone pairs. Do I need brackets with a charge? Nope, he didn't gain or lose anything, so that's it. However, he's got 2 other possibilities. So I can move that double bond to the top, and I can move it to the right. So resonance is about changing locations of electrons only. So you have to keep the atoms in whatever order that you have them in. And now I'm going to make this one my double bond. I'm sure you're getting the hang of it. Just word to the wise, make sure when you're doing your lone pairs, especially using a stylus pen, you really have to put a little pressure on it to make those dots a little darker than usual. Okay? What if we took the same formula but now gained 2 electrons. Let's see what happens to it. Let's check out the math. So we'll do it up here. Na, O, and S. So we know the beginning part's the same. It's what he has available. So 6 plus 6 times 3, and then remember he's going to gain 2 electrons. So 18 plus 2 is 20, plus 6, so 26. So subtract, and now because he gained 2 electrons, you only have 3 bonds. So by gaining those electrons, you lost a bond. So the question is, will this structure have resonance? 3 oxygens, 3 bonds, will it have resonance? And no, it won't, because there is no doubles or triples. So I'm going to have to add my lone pairs around every oxygen. And because there's no doubles or triples, they're all going to have the same lone pairs. But do I need lone pairs on sulfur? Well, right now he's looking at 2, 4, 6, so I definitely need lone pairs. So because he gained, he still needs a charge, so he still needs the brackets. Seen this question before on AP, where you had to draw or look at 2 structures, and you had to talk about the length of the sulfur oxygen bonds. So which is predicted to have shorter sulfur oxygen bonds? The bonds that are in SO3, the ones right up here, or the one with the ion? The one without the ion, because there is a double bond, will have a shorter distance of bond because he's sharing more electrons in that region. All you have is single bonds. They're going to be longer. So because you have all single bonds here, these are longer bonds. So which is predicted? The one that has this one right here, because you have second order bond order. Actually, I should put second bond order. I put the word bond last. Bond order and first bond orders, whereas this one only has 3 of those first bond orders. So because this one has at least a double bond, the length between one of the sulfurs and oxygens will be a little bit shorter than the others. Okay? So use your pictures as evidence. Anytime you're asked to explain, pictures can be your explanation, but you have to include something else with your picture. So it's what we like to call, it's part of your evidence. Okay? Let's try another one, HCO2, -1. And let's do a little NAS. This one we have 3 different elements. So don't forget hydrogen. He does not need 8. He only needs 2. Carbon and then oxygen, but times 2 because there's 2 oxygen. So I have 8 plus 2 is 10, plus that's 16. So 26 electrons I need. But I only have 1 for hydrogen, 4 for carbon, and 6 times 2 for oxygen. Okay? And because I don't want to forget, I put my equal sign way too soon, I gained an electron. And because I gained an electron, I'm going to add that +1. So right there, it's because I added an electron. So I have 12 plus 1, 13, 14, and then +4, so I have 18. Going to subtract, divide by 2. So I got 4 bonds. Okay? Oops, 4 bonds. Now who's the star of the show? Never, ever, ever hydrogen. So then you go to the next element, and you know it's carbon. You know he loves to be the star. Now you have options. When you have 1 hydrogen and 2 oxygens, you want to have the oxygens away from each other. So remember I said, when you have options, then get them away from each other. And you can put the hydrogen on top or put the hydrogen on the bottom. I got to have at least 1 bond between each one of those atoms. But now the question is, who's the 4th bond? Do I put a double bond for hydrogen? And please, I hope that's somebody screaming at you, no, never, ever, ever. Okay? Hydrogen can't do more than 2. He's got his 2. He's happy. Leave him alone. So that means one of the oxygen has to have a double bond. Okay? So maybe I'll pick that one right there. This one was sharing 4. Now he needs 2 lone pairs. This oxygen is only sharing 2 with carbon, so he needs 3 lone pairs. But what about carbon? He's got 2, 4, 6 with hydrogen, and then the 8 over here with this oxygen. He's good, so leave him alone. Can I do resonance? And how many? Yes, I can, but I can only do 1 more. All I can do is move electrons from this oxygen to this oxygen. So 1 more picture only. Never ever will you ever see a hydrogen with a double or triple. It just doesn't make sense, ladies and gentlemen. And it kills me when I see students lose the easiest points on the AP test because they're not remembering what's the basic rule for hydrogen. He's got 1 valence. The most he can ever get is called 1s2. And 2 is all he can get to. Okay? So just remember those key facts. Oxygen looks good on this side. Oxygen on this side. Hydrogen is still looking pretty. And I need my little charge on the top. Resonance is very easy because if you can draw 1, ladies and gentlemen, you can draw them all. You just got to remember, check the octet. Check for the 8. Another way of looking at this is to say that the rules for drawing Lewis structures do not allow us to have a single dominant structure. So you always have to ask yourself your questions. Okay? Do I have any doubles or triples? And if you do, then you have to draw resonance. If you don't, then no resonance. Okay? Can the double or triple be moved to another location? If it can, then it can. So I found these questions from past APs and simple questions on, are there examples of resonance structures? So can the following have another possible structure? So CO2, oh, we know it can. We know it can, we know it can, because we've already drawn it 3 times now. I can make a triple with a single. I can even make a single with a triple. Okay, and I did not draw the lone pairs. Okay, so don't yell at me. I did that on purpose because I was trying to do it fast. Can HCN, can I move any of these electrons over to hydrogen? And that better be a big fat no in your head because it can't. Hydrogen cannot. Okay, can only hold 2. He's done. Okay, what about SO3? Well, if you were just paying attention about 5 minutes ago, we just drew this bad boy. And I can move this bond over here, or I can move that double bond over there. So yes, I could have 2 more possible resonance structures. Can I do a resonance with this? Well, I have oxygen with a double bond. Can I move any extra electrons to hydrogen, or could I move it to this hydrogen? And same thing, that's got to be like an alarm in your head saying, no, 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 can't do that, Rodriguez, can't do it. Okay? One type of resonance structure that can bond atoms together in what's called a ring shape. And we call these cyclos. Okay? It's when you can actually combine all the carbons together in a ring. And they have a certain name, and you've seen this name before, called alkanes, okay, back in chapter 2. And organic chemistry does a lot of this, okay. So with this one, because they have double bonds, they actually have another name besides A and E. These are what we would call single bonds. When they do double bonds, we call them alkenes, E-N-E. Because that means they have double bonds also in it. So this is a special type of compound called benzene. And he has been known to pop up, not a lot, but he's been known to be drawn somewhere on the AP test. And resonance structure is an important concept in describing organic molecules. Organic is any molecule when carbon is the star of the show. Aromatic are these ring structures. Okay, so that word right there, aromatic organic compounds, those are called ring structures, cyclos. And benzene is one of the most famous ring structures out there, C6H6. The 6 carbons are bonded together in a hexagon type of pattern, and 1 hydrogen is bonded to every carbon. We can write 2 equivalent dominant Lewis structures, and what happens is, check it out from this one to this one. If I move the double bond to here, now I have it right there. And if I move this double bond to here, now he's at the bottom. And if I move this one over here, then it's right there on the left side. I didn't have to go clockwise. I could have went counterclockwise, and I still get the same structure. So in this case, with benzene, he only has one possible other residence structure. Note the double bonds are in different places in 2 structures. Each of these residence structures show 3 carbon-carbon single bonds and 3 double bonds. No matter what, you still had 3 on this side, you still got 3 on the other side. You just put them in a different location. And that is the definition of residence, moving electrons around. So I wanted to make sure I got benzene in here because I don't want you to see something like this on the AP test and you just start kind of freaking out. Experiment shows that all 6 carbon bonds are about 1.4 angstroms. Remember, angstrom is how we measure bond length. Okay, so between a single, which is 1.4, and a double is 1.3, they take the average and you get about 1.4. Not something you have to know, but remember, if you have double bonds, you have 3 single bonds and 3 double bonds. So you have 3 first order bond orders, and you have 3 second bond orders. So remember, in the end, it's a blend of 1.5 bond order because you have equal amounts. Okay, you can't say that for something like this. Where it was this structure right here where you had 1 double and 2 singles, you're not going to get a 1.5. You'll probably get about a 1.3 because you have 3 different areas over here in this structure where 2 of them are singles, 1 of them is a double. So you'd probably get about a bond order of about 1.3. Okay, so not exactly 1.5. Okay, so I just put in some information about benzene. We have also seen benzene where they pretty much omit the doubles and single bonds. So see right here, you can even draw a circle instead. It's about the only time, ladies and gentlemen, we are ever going to talk about ring structures is today. No other chapter ever. I just wanted you to see the ring structure called benzene and how it's formed and how it can also have residence structure. So this shorthand notation right here, shorthand notation is sometimes they draw a circle instead, where the doubles can be on the top, bottom, left, and right, or it can be on the top, left, and right, and bottom. So they just draw a circle instead. Okay, this is a big thing in organic chemistry where we draw and we do residence galore. Okay, so if this is something that you think is super duper fun, organic chemistry next year is for you. Okay, so I know you'll definitely love it. With organic compounds, this is pretty much where biochemistry and pharmaceutical, anything made with plastics, stuff like that, you would see these type of structures, especially the hexagon type of patterns. They are all over the industry. Doc Dina has some examples to help you, and right here also to practice your benzene structure. So I did put her video up here, and I know how much you love listening to Doc Dina and her explanations. I put it on here today, so you will see it labeled as 1.6, I'm sorry, 8.6, there it is, 8.6 Lewis dot structures. And it's just a way, ladies and gentlemen, one, you get a little break from Rodriguez's amazing voice, but you also get another perspective. You get another person that also teaches you. And if I can get it across to you, or if she can help you with this, whichever way helps you the best, then focus in that direction. Okay, so I always try to give you other perspectives on how to explain stuff. Okay, 8.7 is when